Generalized Linear Models with Examples in R, that book right there. And we are on question 4.5 in chapter 4. Okay, so this question is very similar to question 4.4, but whereas in 4.4 we were doing things like finding the likelihood and log likelihood, score function, etc. for the normal, for the mean parameter mu of the normal distribution, here we are finding the mean parameter. Here they call it mu, sometimes it's called lambda, but nevertheless, we're finding the mean parameter for an exponential distribution, which is a density function that looks like that right there. But we're basically going through all of the same steps. So this is very math heavy, and so I encourage you to go to the Colab sheet. There should be a link in the description, so I'll just give a cursory overview, and if you catch mistakes, then do let me know, and that way I can make the corrections on the Colab sheet. And so instead, what I'll do is I'll just kind of give a narrative overview rather than walking through all of the details. Okay, so the part one is we want to determine the likelihood function and the log likelihood function of our density. Okay, so remember that the likelihood function is really just the product of each observation, where each observation comes from, whatever distribution. Here it's the exponential distribution. And so, you do the math and eventually you simplify it, and here it looks something like this. And of course, the log likelihood is just taking the log of the likelihood. Okay, that's all it is. And again, the reason for this is that when we set to trying to maximize or minimize this function, well, the maximum of this function, which would be the most likely value given the data, whatever that value happens to be is going to be the same on the log scale. Okay, and so if we put it on the log scale, because the log scale uses a bunch of addition rather than exponentiation, stuff like that, so it becomes easier on the log scale. Okay, so that's the motivation there. Again, just let me restate that. We go to the log scale because ultimately we're going to want to maximize this function, and the value of mu in this case at which the log likelihood is maximized is the same value at which the likelihood is maximized. But because the log likelihood is simpler to work with, we prefer to convert it to the log likelihood. Okay, so now we go to the score function. So what is the score function? The score function is simply the first derivative of the log likelihood. Okay, and so we take the first derivative with respect to our parameter of interest here, mu, of what we found is the log likelihood, and we churn through that, and we get this expression. Okay, or maybe this one, somewhere along the line. These are all equivalent, but this is where I simplified it to. Okay. And now, with the score function, we will set to finding the maximum likelihood estimator of our parameter of interest. Again, here mu, and so this is where we're, maximizing the function. Okay, and so now we take our score function that we just found and we set it equal to 0, right? Because again, where the first derivative is a maximum, where the first derivative equals 0, you're either at a maximum or a minimum, and because of some conditions that are generally in place for our standard probability distributions, 0 is a maximum. Okay, especially in a univariate type of a distribution. Okay, so but again, all that we're doing is we set the score function equal to 0. And then we just set about trying to solve for mu, and now, but it's actually mu hat, okay? In this process, I never quite know where to call it mu hat, right? So here it's mu, but we're trying to find an estimator, and our estimator is this. So I think that probably this should be mu hat, but yeah. Okay. Okay, and so now we have our point estimate for the parameter of interest, but we might also like to know, how certain are we of that? In other words, what is the standard error of our estimate for mu. Okay, and so so we will get there, but the way that so we'll get there in part 5. But the way that we get there is by utilizing the expected information of everything. Okay, so what is the information? So what is the expected information? Well, the expected information is the expected value of the observed information. Okay, so we need to find, we need to find the observed information and then take the expectation. Okay. Okay. Well, what is the observed? Information? Well, that is just the negative first derivative of the score function, or stated differently, remember that the score function is the derivative of the log likelihood. So we could also say that it is the negative second derivative of the log likelihood. Okay. Sorry, my cat is being very loud and annoying, but we'll just push on here. Okay. So so again, we work through that derivative, the negative derivative, I guess we should say, and we get this, and then we want the expectation of this value. So we wrap it inside of the expectation operator and go through the expectation operations, and we come out with this guy right here as the information, the expected information. Okay. And so now with that, we can find the standard error of our estimator. Okay, and so it is, well, it's this, right? It's 1 over the square root of the information, right? So I take I take my information matrix, put it under 1, right? Because we're taking the inverse, and I take its square root, and ultimately I come out with this expression right here. Okay. All right. So there's all that. And so all of that is just us getting an estimate and some kind of bounds of uncertainty about our parameter of interest. And now we want to do some hypothesis testing, and we have 3 ways to do this. And so we have the Wald statistic, we have the score statistic, and the likelihood ratio test statistic. Okay. And so here the answer is given to us for each of these. It says show that W, or the Wald statistic, is this, the score statistic is this, and the likelihood ratio statistic is this. And in each of these cases, we're using mu equals 1 as the null hypothesis. Okay. And so again, I'm not going to bore you with the math. These are just 3 different ways of testing a null hypothesis about our parameter mu. Right, and again, the null hypothesis here is that mu equals 1. So we're going to test our mu hat, our estimated mu, against the null hypothesis. Okay, and so these are just the formulas, and we work through. And in each case, you see, by walking through this, you see how we get to the the prescribed formulation of that statistic. Okay. Yeah. Okay. So there's all the details, and then finally in parts 9 and 10, we want to plot the 3 statistics that are just calculated for different values of mu. I think this should be mu hat. Okay, the book calls it mu, and I'm going to call it mu, but I think it should be mu hat. Okay, and then we want for sample sizes of 10 and 100. Okay, and I've just reiterated the the formulations right here. And the book actually, the back of the book gives very nice code for this, and so I think that we'll just use that. We're also supposed to comment, but that's very, very vague. I have a tough time understanding exactly what we're supposed to comment on. But if we look at these with the sample size of 10 versus 100, we see that they both. Okay. So there's a few things maybe to comment on. One is, notice that they both share the same x range. Okay, but the y, so the n equals 100 is much larger, right? And so this means then that there's more information being contained in the n equals 100, right? Because in order to cover the same x distance in a much larger y distance, then these, I'll call it the slope, it has to be much greater for each of these. So that's one thing. Next thing to notice is that the three estimators, regardless of sample size, converge on um, the the null hypothesis, but that as you move away, that the three statistics disagree. You know, you know, they give different values, right? So the, you know, like the Wald statistic gives a different you know, a different value as you move away from the null hypothesis than does the score function or the log likelihood ratio test. So I think that is it.